us a couple of summers ago. And so I'm just going to give an overview of how it's formulated right now and sort of why we need it. So this is a picture you've seen a couple of times today. So we want to sort of automate this force field building scheme, and so I'm going to focus on the quantum chemistry and uncertainties in the top. So this is not just a straight in out, we have a single conformation, we have a single energy, but we actually need to think about the uncertainties of the energies that we get. So let's say we have this molecule on the left, this alcohol here, and I'm showing two different conformers A and B. So two questions we might want to answer if we're thinking about the energy landscape of this molecule is which conformer has the lowest energy. And so if you think about it, so the oxygen on the left actually has this hydrogen, so there's this intramolecular hydrogen bonding, so A is actually lower in energy. But then you might want to figure out what is the energy difference, and let's say you do one QM method and it says 4.2, and you do another QM method that says 5. Well, how do you know which one to use? Because let's say both QM methods are of comparable reputability, so can we somehow incorporate both of these answers? And so this is sort of where the pipeline comes in. So I'm demonstrating on this example molecule. So we input it as okay. There's supposed to be text underneath. I didn't translate well to PDF. So you input it as a smile string in the first box. And then from the smile string, you generate conformers using OpenFF omega. And then so that's the red, white, and blue structures. And then once you have this wide set of conformers, you want to filter out and remove any redundant minima, because when you actually want to send these through QM calculations, you don't want lots and lots. And then so this first stage here actually also has a quick optimization using steepest descent. And so, for example, without that, I might have 30,000 conformers, but with that, I might whittle that down to 100. And so then we have two levels of QM, the first one in the left, and then the second one in the right. And then the first one, I'll go over a little bit more detail of why we need that later, but the second one is what we want to focus on, and this is where we consider a bunch of different methods of comparable, relatively high accuracy. And then we are comparing the energies of all these, and then these will be used, the energies in the parameters and the uncertainties will be fed into the force field building pipeline. So here I showed 3 optimizations in this pipeline. So with the steepest descent, I already kind of used it to describe, we just want to get closer to the minimum. For the second one, in this case, we're using MP2 with the relatively small basis set, and this is all done in Sci4 version 1.1. And so the purpose of Kickoff is to fine-tune the geometry such that you don't have to spend as much time doing many different fancy ops that are a lot more costly. And so here I'll show the results. In this case, I looked at 10 to 12 different fancy ops. And in actual practice, we're going to focus on 3 to 5 different levels of theory for the fancy op, and then consider that for the uncertainties. So I tested this pipeline on a bunch of different molecules. This is a subset of what I have, and this is my diverse set. So here we see alcohols, charged species, some potential pi stacking interactions, hypervalent sulfurs, here's a Zwitter ion, and some planar pyramidal competition intramolecularly. So I'm going to focus on the first molecule, which we saw earlier. So here, these are the same conformers that you've seen, and so here we see that D, which is the one that has that intramolecular hydrogen bonding conformation, is indeed in lower energy, and S is the one that is in higher energy. So this is with these are the relative energies of one particular method. This is MP2 with the OGCC-PBTZ basis set. So how does it look like if we consider a lot of other different methods? And we see that the results are actually pretty similar, which is pretty good. And so these are all the methods I looked at. And so there are 2 takeaways from this plot. One, that you can see the trend in the relative energies, and it slightly increases as it's further from the minimum. And the trend is consistent in different species, or different methods, like I said earlier. So I wanted to quantify how different a method was from another. So here I'm using it as a reference. So I take all the minimum found from the MP2 OxyCPBTZ method, and I want to see how another method might compare. So you can see here on the plot, the orange pluses are a little bit higher as well as the light blue circles. So let's focus on the orange pluses, which is the MP2 631G star. So we would expect that the orange pluses has more deviation from my reference method. And so that's sort of what is being displayed in this heat map plot. And just to make it a little bit easier to see, so this is basically a 1D representation of everything we saw in the last set of line plots. So a color that's more purple is more different from the reference, and the reference is on the x-axis, and a color that is more green is most similar. So in this plot, we see that the diagonal is dark green because it's basically a self-comparison. So we see here that two of the purple methods, one of them is MP2 631G star, and this other purple method was the light blue color, and that one was the orange pluses. So we can see that looking at all of them together, basically doing an n-by-n comparison, we see that all the methods are pretty close to each other, and I would say this is because this is a pretty simple molecule. This is only a few atoms. With the other molecules in the diverse set where we have, for example, potential pi stacking, we might see deviations up to 5 kcal per mole. And so another thing I wanted to look at is, if you remember in the pipeline, we have a number of different fancy ops. So instead of doing a whole bunch of more high-level QM calculations, we wanted to see if we could use single-point energy calculations to sort of reproduce that higher-level energies. And in short, the answer is no. So here I compared what is the energy of just doing the single point before the optimization, and then what is the final energy after optimization. And we can see there's deviations up to 4 kcal per mole, which is pretty high. And so here, the most outstanding molecule in terms of this is DIB2, and for this case, why that happens, here's another view of it. So basically just plotting all the 12-ish molecules, and here is the main outlier. And so the big difference in this is we see that there's a charged oxygen on one end, there's a hydroxy group on the other end, and what actually happens in the higher level QM calculation is that it kind of collapses to form this intermolecular hydrogen bonding structure, and so that gives a very big energy difference. And going back to this plot, most of the methods actually do this. So most of the methods actually do this, and this is not limited to this molecule. So div4, which is this column here, has the potential pi stacking, so it rotates some of the rings for better energetics. So we don't want to stick with single point energy calculations. We do want to do the full set of optimizations for fast op and fancy opt. So moving on, we want to focus on the 3 to 5 methods that I mentioned earlier to actually quantify the model uncertainties.
Okay. I'm sorry. Can you just go back for a second? Mm-hmm. You might have said this, but wouldn't the simplest thing be just to put some restraints on the torsion so that it can't flip around?
Yes. So we did think about how can we control for these edge cases, if you will, but going back to the bigger picture, we want to do this for many, many different molecules and many, many different conformers. So this would take a lot of human time in terms of determining what would be an appropriate, constraint or something for the optimization. So we decided to choose a method that was more generalizable for most things. So we decided not to do any special treatment for these type of molecules to reduce the human time that it would take to figure out what the problem is, right, and then what is an appropriate restraint.
So I'm sorry, I may have totally spaced out, missed it, but you do want it to change conformation, or you don't, in a sense?
It's not that I do or I don't. It's that so we're looking at so we have this fast QM optimization, right, and we're looking at do we need the second level of QM optimization, or can we just use that method and calculate the energies?
And so what did you conclude?
So I concluded that we can't just calculate the energies without doing the second additional optimization.
But I thought the second optimization gave you more trouble because it generates heterogeneity in the confirmations, because some flip and some don't.
Right.
So then you really can't compare. So either you want to do single point or use restraints.
Yeah.
You know?
So the comparison is not an issue because going back to this, so basically what I do is I take the results of this method and I say, what are all your minima? So the unique minima. And then I go through all the other methods and I find the matching minima by an RMSD comparison of the geometry.
Right.
So even if they optimize to different minima, I'll find whatever one matches it in geometry, and then I look at its energies.
So to put it another way, we're after getting the correct right answer for all of the minima with the fancy optimization level of theory. As a shortcut to that, we were asking if we could get it without having to re-optimize at that level of theory. And we find that, well, the fancy optimization level of theory sometimes makes these things collapse, and we might not pick that up at the lower level of theory that we're using for the quick optimization.
Okay.
So we do need to do the full optimization.
But then if like one fancy one makes a collapse and another one doesn't, you have to go back and make sure that everyone gets done on equal terms. Or I mean, it depends what you're trying to do, right?
Right, it depends on what we're trying to do.
Right.
In our case, we would want to know that one doesn't and one does, I guess.
I mean, that just might be some vagary of the potential surface at the starting point. That other minimum might still be a lower minimum. It just might not have managed to get there due to the optimization.
Yeah, so to some extent, the way she's doing this analysis controls for that, right? Like you're doing a sort of RMSD comparison.
Yeah, so I'm determining which geometries go to which among the different methods.
Mhm.
Is the main difference between quick opt and fancy opt the chosen QM method? I might have missed that.
Yes.
So, what is quick opt then? Is it one of those?
It is not on here. So all the geometries on here started from quick opt, and this is level 2. So quick opt is this.
I see.
Yeah.
Okay, thanks.
Mm-hmm. Okay, so what I've been working on is sort of how do I improve the efficiency of this pipeline. So point 1, I already talked about looking at the energies before and after. So next we want to look at different levels of theory for the quick opt. So we chose this one when we just compared like 5 or 6 methods on one molecule. So but we want to see if it will generalize to the diverse set. And then secondly, want to look at the quick opt efficiency and see, so for example, with quick opt to make sure that the inclusion of this additional QM optimization indeed lowers the runtime overall. So I think that's everything I have.
Any other questions or discussion on that?
So what is it we want to be doing with the QM? I think that's a big question in my mind, is that do we want like the square minimized structures? Do we want a lot of diversity in structures so that we crawl up the walls and learn something about the curvature? I think we have a variety of different uses that may demand different kinds of...
And it seems very related to the torsional scanning.
Yeah. Which we may not even want torsion scans. We may just want lots of random structures and lots of perturbations on those instead.
But given that this is minimization based, that may not crawl up the walls and give you those.
Yeah,
Sure.
This is the
things.
Vicky didn't get to go into this much, but if you want to put back up the relative energy plot
Yeah.
variation. So part of this was about, as part of this Bayesian framework, we need uncertainties in the data we use. And for QM data, we don't have those uncertainties unless you count numerical uncertainties, which are ridiculously small. So our thought was sort of, well, you could say these are all somewhat reputable, so you could say, well, that's kind of the uncertainty in some sense, or at least that's gives us some notion of the uncertainty. Like if you ask what's the energy of this conformer relative to that conformer, well, you can see there's considerable variation across those methods, so at least gives us some idea of how well we know.
That's more of a measure of disagreement amongst reputable experts, right?
But
That's right.
Difference from experiment.
Okay. Yeah, but so it's not a difference from experiment, but
It's still a model uncertainty.
Yeah.
But it may not. Like, what, are we trying to optimize for Yeah, just
But we don't have the ability to do arbitrary experiments, whereas we do have the ability to do arbitrary QM calculations. So I feel like it's the best proxy we can come up with unless we have the ability to do arbitrary experiments.
But I mean, isn't if you don't like your B3 libs don't all have dispersion corrections. At least one of them doesn't.
Yeah, so
Right.
in this case, we were looking at different dispersion corrections. And
Right.
so, for example, these two, the TZVP basis sets, one of them has this M and one of them does not.
Okay.
So we see that both results of these are pretty similar, but there are cases where they
What, the
differ.
third one from the bottom has no dispersion.
Yeah,
Yeah,
this is
B3
a-
libs
Apparently,
And
when
is
I
that
went
one
to
an
the
outlier, or is
HTML,
that
I
actually
used
something?
It is, so
It's
this
new.
is the orange, so it's sort of in the middle of the range.
I guess I just have the feeling that if you're among quantum chemists, there really are some methods that are better, and not all of these are equally good.
Yeah, I mean,
And then
there
the
is a
other two-
limit, right? There is a real unambiguous
Well,
basis
there's a-
set and
Here's the
theory limit.
thing, is we actually had a paper where you can get full CBS couple cluster results using focal point analysis for quite cheap. So we could actually run that on this. without
Okay.
too much time.
So that would be,
Um,
maybe that's something you can touch bases with me about after
because like
this.
that would be, in terms of quantum chemistry, about as good as you can possibly get. And
Because then we'd sort of be after like saying, okay, what's a good method that will get us kind of close to that routinely,
But
but then
also
also
be fast.
but then also we can spot check occasionally to get an idea of uncertainties.
But I think,
And-
sorry.
And that's exactly kind of like what you want to do.
Yeah.
It's like, it'll vary from molecule type to molecule type, but you can get the QM answer.
Yeah. And then we could imagine like building a database of like uncertainties by functional group or something that we,
Or just
some kind of
machine learn them or something.
machine learn the uncertainties.
But if I,
That would be fun.
I'm sorry.
if I remember correctly, getting the focal point analysis, the CCSDT geometry optimization is not that routine right now, right? I mean, gradients do exist, but not many implementations of them. So do the geometries still come from MP2 usually?
Yeah, so what you can do is like you do the focal point analysis. So a couple of cluster gradients, and we have them in Sci4 these days, and they're relatively fast. And so what you can do with them and like CCP easy even, and add that to like an MP2 extrapolated gradient and get near CBS results. I think the paper on that's going to come out in like next month or so. Actually.
Cool.
Can I say so? But the discussion that I think you're having is saying you're saying there's a really not all ab initio methods are the same, or not all electron structure methods are the same. Some are better than others, and here's a really good one. We should use that because it's really good.
It's going to be really expensive though.
Right.
Yeah.
But what I think a point that John made rather forcefully while I was on my sabbatical was that how do we know how good is a QM number? And one can ask that with respect to an experimental result that we don't have and can't get. But one of the points that I thought you were making, John, was how do we know the number is just even as a QM number? And I think this begins to tell us that that's some kind of model uncertainty. Look at Koffner number n. It's about 2/3 of the way long, n. See how there's a low, that green point is pretty low, it's like an outlier. Look at the level of that method. That's B3LY, a hybrid functional, all dressed with the
But is that good or bad? Maybe all the others are
that's
wrong.
good, and all that alphabet soup for the basis set there, that's about as good as I see on that slide.
The B3 lib?
The
B3
green
with
outlier on the
D3
bottom, yeah.
That's as good.
BJ with
Yeah, no, I wouldn't have
Def
thought that any B3 lib would be as good as the RCC blah 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 at the top.
and these are the kinds of conversations that we have. You see, maybe B3
But if we can
Not
get
that
the
I remember.
limit, right?
Yeah.
Why don't we
Well,
just want the
no,
true answer?
But my point is that the one that's the outlier is
Uh-huh.
actually a pretty good one in that case. I'm trying to make the point that you were making quite forcefully a couple of summers ago,
But-
that these models differ, and we need to get an idea of how much that is.
Right. But
And I think this does that.
we can't. If we can reach the limit, then
Yeah.
that's it. That's the
That's
that's the answer.
Because if you can get the delta between the limit and these approximate methods, that's going to tell you more than the spread of these approximate methods.
Well, John, that QM limit that we get, how good is that?
Well, it's the real thing for the gas phase result. It's
Well,
literally
it's only as
the
good as our QM method. These were points you were making.
no, but all of these we have no idea what the error is to the
these are
true
all-
limit.
in
Well, what's
comparison-
the error on your super accurate?
It's 0.
Yeah, I mean about 1%.
Well,
I mean, in terms
Some
of
of these
like,
things could be
electron
tested by
condition.
gas phase things, maybe this microwave.
all I'm trying to say is we can get, Vicky can get a practical number with some, what are the chances that your super accurate method would fall within the envelope of values that we already have out there? I bet you it's pretty good.
The point is we don't know. Right?
Well,
We don't even know
No, we
how
should check
different
that.
it is. Yeah.
And this is,
Well,
I have a
that's-
feeling that there's a slightly different issue that's also important. Maybe I'm wrong, but I mean, you're doing the optimization. If you use your force field and one of the bond lengths is a little bit off, and you run the quantum, you're going to get this wild energy.
Yeah.
I think there may be more dirt and problems in the subtlety, in the fact that some of these, there's some hardness to these conformations. And there's some degrees of freedom
Yes.
where if they deviate a little bit, your energy will be wildly all over the place, and you may get. There was a long time ago. There was a paper comparing force fields with quantum for some gas phase peptide things.
Mhm.
And I think there were really bad discrepancies, and people said, the force fields are really bad, and it's gas. It's a whole discussion, but then I think somebody else said, well, if you do a little bit of minimization with the force field before you do the comparison, it gets a lot better because, or maybe with the quantum, basically one of them, the ideal conformation from quantum is a little bit different from the ideal conformation for the force field, and they see each other as being high energy.
Right. But these are optimized at every point, right?
Yeah.
Yeah. So that
I guess what I'm getting at is that I just there's a possibility that the conformations that you throw into this thing, you say I wanted my force field to agree with the quantum, and it's going to disagree really badly, but just because your equilibrium bond length is off by 0.01.
Of course, and that's the
angstroms.
main contributor. Like if you wanted to do QMMM, right, and you were reweighting from MM to QMMM, that's what throws everything off, is that small discrepancies in the valence terms. We could fit for a specific level of QM theory if you wanted to do QMMM. That would be the right thing to do. But if we're trying to get something that's representative of reality, it seems like we do want to quantify what the expected uncertainty is by looking at what's the true error or the extrapolated true error.
So I think there's sort of the big question here is, so I think we all agree we need a QM database, and we're going to do lots of things with this QM database. And also for Bayesian fitting, we need uncertainties even on the things in the QM database, unless they happen to be the exact right answer.
Or we can use the QM database to estimate what the uncertainty should be for particular application classes, right? We don't need to attach to the QM database.
You mean, like, for example, for what application classes? Trying to imagine.
Well, if we're going to use these in a Bayesian inference context, right, you would want to have some idea of you're going to have a very small number of limit calculations, right? Not for every one of these, and a very large number of practical calculations from which you will derive some general estimate of uncertainty that you can plug in.
Right. So I guess what I was going to say, and I think you just answered what your answer to part of my question is. We have sort of two options. One is we say, well, everything in our QM database is going to be just the right answer,
but that's
which is going to be too expensive. Or the other one is the things in the QM database, some of them are going to be the right answer, and other ones are going to be wrong, and we have to figure out estimate the uncertainty somehow.
But I think
and we're looking at a way to estimate the uncertainty, which isn't bad at all. In other words, Vicky,
and so I think
you have an uncertainty which you could estimate for whatever's the model you're fancy.
I think what they're saying is that we could also estimate the uncertainty by just saying, look, let's get the right answer for these guys and see how far
any
off
relation whatsoever
that falls from these, and then build a model for the uncertainty. And so I think our feeling is, well, probably the right answer is going to fall somewhere in between here, and we could get some estimate of the uncertainty from that, and their answer is no. So we should find out.
I guess I'm also wondering whether I'm back to my little bond length thing, that if you did these, couple cluster, and you did optimization of a couple cluster, and then you did the same thing with a relatively high level but not as good thing and optimized, and you just swapped coordinates and calculated, would you have the same hard degree of freedom problem where if you then did a very localized relaxation with the torsions tightly restrained, they would look a lot more like each other, or at least conformational energy differences would look more alike. I just wonder whether that hard degree of freedom issue can also generate maybe a deceptively large amount of scatter.
I think this is when you're optimizing every point, simply because for every single one of those methods, the energy surface looks different. So,
Right.
You can't just hop.
But they're optimizing it without putting torsional restraints, so sometimes it's flopping around. So I sort of lost track of what we're comparing, which maybe might just not having listened carefully. But,
Yeah, we are being careful to
Uh-huh.
match up the conformers
The
to
minima.
make sure that they're still close
Yeah,
enough that we
sort
can
of the
call them
same
the same.
conformer.
conformer.
Yeah.
Yeah.
And when I say the energy surfaces are different, I mean you're talking about tiny perturbations between them. So it's not like you're going to get like a completely different minima.
Yeah.
It's just that it's small changes.
I think that even if the potential energy surfaces are different by a tiny amount, it is still possible to get wildly different minima, because what prevents you from seeing as was pointed out earlier, what prevents you from seeing a collapsed structure versus an open one is not that the collapsed minimum doesn't exist in one method. It could be a barrier difference, a barrier of 1 kcal per mole or 0, or just the optimization took a slightly larger
Yeah.
step, right?
So
The results are algorithm dependent.
So some methods lose conformers, for example. We don't have any. There's no examples of this for this molecule that I see, but some of them lose conformers.
Yeah.
I think we should probably wrap up there.
Well,
We have-
just before we do, I want to make another point about torsions, because this is going to come up. We've alluded to torsion scanning and getting away from torsion scanning. So I want to just say, look at these 20. How many?
It's about 19.
18. Look at
19.
these 18 different minima, and there's a couple of torsions in this molecule. So all these different minima are actually, as minima, they are scanning the torsions. They're not going to scan all the values of all the torsions, but the minima for this one molecule are going to, in and of themselves, represent some partial part of the torsions that we would want to evaluate. So imagine a torsion parameter that we want to, a torsion that we want to parameterize in many molecules, just with the minima that we would get for using for all our purposes, they would actually, as an accretion, serve to give us a torsion scan without actually having to scan any torsions. That's what I was going to suggest that we use.
So, but we need more than just the value at the minimum, right? So we need something that crawls up the walls a little bit to get the curvature.
Unless those minima are crawling up the walls a little bit.
Yeah, I don't think they'll do enough of it though.
Well, beg pardon?
I don't think they'll do enough of it though.
Well, and if they don't, then we can do some. But I'm saying a most efficient use of QM effort would be, instead of spending, how many points were you doing on one torsion scan? 24 points or something like that, 24 points? Instead, look at the accretion of minima we already had in our
Yeah.
QM database, and then evaluate the 4 or 5 crawling up the walls things we actually need.
So what if we also stored all the points on the way to the minimum? Because
Yeah.
that
Yeah,
gives
that'd be
us
perfect.
information about the curvature,
I totally agree, absolutely.
and it's free.
And-
Don't throw away data.
Yeah.
And I see that, and I raise you the fact that we may not, if we are using gradients, we actually may not need to go all the way to the minima. If we use the value of minima is that you know the gradient is 0, and so you can use that, you can fit a minimum to a minimum. If you're actually going to keep the gradients, in fact, you might be able to save you many cycles by just going a few steps down in optimization until you're well into the harmonic regime. You're a very small distance away, but save yourself the extra 5 steps because it amounts to less than 1/4 of a kcal per mole. The geometry is really similar. You've got bigger fish to fry in your force field.
Mhm.
So then you can have very efficient gradients by just truncating doing a dirty minimization, basically doing a dirty optimization. But I mean, this is now engineering. It's
Well-
about being efficient.
There's also forces too, right? Forces give us a lot more information.
Yeah, that's the
It's
gradient, right?
Yeah.
Yeah.
So
You're saying store the gradients as well as the
yes, and fit to them.
energies. Yeah.
Fit to them. Fitting to something that's close to the minimum but not quite there, and including the gradient in your fit, is probably going to be about as good as fitting to the minimum, which will cost you twice as much energy. So, but I wanted to just stick on this slide because I wanted to look at all those minima and consider how much of the torsion scan, how much of the values you're trying to scan is actually already embedded in the minimum. So that was the point I was wanting to
Thanks. So I think what we should do, since we won't get to much planning today.